Hi, my name is Mohammed Tariq, and in today's lecture, we will build a heap data structure. So, let's suppose if we have a set of data and we want to build a heap data structure, then what steps we need to take and how can we build an efficient heap data structure? We will see that how we can do this. So, let's start the lecture. Suppose we are given as input n keys or items and we want to build a heap of the keys. So the word keys here is actually referring to the nodes. You can think of this as the nodes, or also you can think of this as an object. Let's suppose I have an object with some image, or you can say some binary data. So how can I get the priority of this object? So I need to attach some keys with that. So so the word key is actually referring to that. The second point is obviously this can be done with n successive inserts. Each call to insert will either take unit time or log n. So what this actually means is let's say I have this data, right? This data is a random data and I want to create a min heap, right? I want to create a min heap. So to create a min heap, what I can do is one approach is let me create another array of the same size that I have, and then on every insert I will check is this violating the min heap rule, and if that insert violates the min heap rule, then I will apply the rule. For example, 65. Let's say 65. So I have this node as 65. So let's insert 65 here. Okay. Then I will insert 31. Now 31. And now I will check is 31 less than 65? Yes, it is less than 65. So I have inserted 31. Okay. Now 31 is less than 65. So I will have to swap this, right? Because according to min heap, the minimum value will be the root and the greater values will become the children. So let me swap this. 31 will come here, 65 will go here, right? And then same case with here. 31 will be the first node and 65 will be the second. Let's say this is index 0, which we are not using. Now next number is 32. So let's insert 32. Is 32 less than 31? No, it's not less than 31, so it will remain here. 32 will remain here. Okay. Now let's insert 26. Okay. So for 26, 26 will come here because remember we are going from left to right. 26. Is 26 less than 65? Yes, it is less than 65. So we will have to make a swap here, right? So 26 will come here, 26 and 65. 65 will come here, 65. Okay. Now 26 is less than 31. Yes, it is less than 31 also. Then we will have to make another swap. Okay. So 26 will become the root and 31 will come here. We will do another check, which is 32 is less than 26. No, 32 is not less than 26. So that's good. We need not to make any further changes. So now after 26, let's have 21 and let's add 21. So 21 will be added here. 21 will be added here. 21. Is 21 less than 31? Yes, it is less than 31. So we'll have to make a swap here. 21 and this is 31. So 21 less than 26? Yes, it is less than 26. So again, this is 26 and this is 21. Is 31 less than 21? No, it's not less than. So there's no swapping. So as you can see here, after every insert, I will have to ensure the rules of min heap. And if there is a swap needed, we are making the values, we are swapping the values, and then we are maintaining the tree as a heap data structure. So after every insert, so actually this I've shown this using this tree. So this actually inserts are going in the array. We can also use the tree also. There is nothing or which restricts us from using the trees. But here we are focusing on the lecture that I have delivered. So we are using arrays for the implementation of heap. So what is the cost of this? So the cost of this, the worst time for building a heap for n keys could be n log n. So how it is n log n? Because I'll have to at least traverse this array from its first element till its last element. Okay, so n traversal is compulsory. Now the number of swaps I'm making, this will also be the part of this cost, the part of the complexity. TC is for time complexity. So I'm doing log n after every insert if there is a swap required. So I'm making that swap. So the log n cost will be multiplied by n. So for example, if I have 10,000 values, I have a set of 10,000 values, then the log n of 10,000 will be 4. So it will be equal to 40,000. 40,000 comparisons actually are required, right? 40,000 comparisons are required to create a heap data structure for the 10,000 elements, right? So can we do this better than this? Can we reduce this cost, or can we have something efficient than this cost? It turns out that we can build a heap in linear time. We have a solution, and how it works, let's see. So I have a tree here. I have the same tree, and the values are the same. I have this set of values, and these values are the same. So this time, what I have done is I've created a tree, and this is an unordered tree. The values are at same places as in the array. So 65 is the first one, 31 is the second one, 32 is the third one, and as you can see, this is not a min heap, right? This is not a min heap. Now to turn this into a min heap, what we need to do, we can do something like this. The algorithm to place the n keys in an array and consider it to be an unordered binary tree. So what we did is we just considered that as an unordered binary tree, right? Consider it to be an unordered binary tree. Now the second part is the following algorithm will build a heap out of n keys. Now using this algorithm, we will build the heap out of n keys. So we are not right now, we are not inserting, or we can say we are not inserting anything in a new array. We are using the existing keys, and then we are trying to build a heap. How we can do that? Let's see. So the program says, or the algorithm says, we will loop till the n divided by 2. We will loop half of the array, and then we will apply move it down. So actually, what move it down doing? Let's see. So I have total number of the elements in the array is 15, right? So 15 divided by 2, I have 7. So I'll get something 7 point something, but this is the integer division, so I'll get the integer value only. So now I have 7. So the next step is, you can see the I is at 7. Okay, in the for loop, the I will be 7. So the for loop is something like for I equals to 7, right? Based on this array. And what we have, okay, I is less than 0, and then I minus minus, right? This is the formula. Now what is I? So I is actually a subtree. Okay, I is actually a subtree. This is a subtree. So what we will do, we will first make this subtree a heap structure. Okay, we will only make, as a first step, we will only make this subtree as a heap structure. And to make this as a heap structure, what we need to do is we will compare the root node with its child, with its children. So we will compare the 68 with 70. Is 68 less than 70? Yes, it is less than 70. Then we need not to make any swapping. Then we compare 68 with 12. Is 68 less than 12? Yes, it is less than 12. So we will make a swap. Okay, we will make a swap. So now in this tree, you can see this subtree is a heap structure now, right? This confirms to the heap structure. Now the next step is we will do I minus 1. So when we will do I minus 1, this I value will be here on node number, on index number 6. As you can see on index number 6, we have this subtree. Okay, we have this subtree, and then we will apply the rules of heap data structure on this subtree. So according to this, as you can see, 5 will be swapped with 19. Now we can, as you can see, we have the I is standing on index number 6, and we will then swap this with 5. So now this structure has been balanced. Okay, this structure has been balanced. Now what we have now next is I is at 5. In the same way, what we will do, we'll do the swapping. 14 will go up, 21 will come down. Now this has been done. This subtree is a heap tree now. Next is index 4 and is 26. Now as you can see, 26 is greater than 13 and 26 is greater than 24, right? 26 is greater than both the values. Now here we will have to be careful, and we will have to make decision that which one is the least one, right? So 13 is the least one. So we will swap this with 13. Okay, we will have to make this confirmation, and we will have to be careful on that, that if the root node is less than both these children, then which one is the least one, and we will make swapping based on that. So now this is done. Okay, now this structure, as you can see, we have completed this structure. These 4 subtrees, 1 2 3 and 4, these 4 subtrees has been converted to heap data structure. But now we will see next what happens. So now the I is at index 3. Now we will have to make this subtree as heap data structure, right? We will have to make this. So now 32 is greater than 5, and it's greater than 12 also. So we will go to the 5 because it's the least one. Then here is 32 now. Now we will check again, is 32 less than 16 and 19? Yes, it is less than 16 and all, sorry, it is greater than 16 and greater than 19. But 16 is the least value, so we will swap 32 with this one. So the final destination of 32 will be index number 12, and 16 will take the place of index number 6. So as you can see, 16 is at index number 6 and 32 is at index number 12. Now same with this case, we will swap 13 with 31. 31 will come here at position 4, and then we will swap this again with position 9, and 24 will go up. So now this subtree has been converted to heap data structure and has been converted to min heap. Now with the root node, now we have the root node, and our I is standing at index 1. As you can see, with the root node, we will first check, is 65 greater than 13 or is greater than 5? It's greater than both the values, but the least one is 5. So we will first make a swap with 5, and then from here we will make another swap with 12. Because 65 is not greater than 68, so it will not be swapped with 68. And now we have our min heap ready. So here we can see we did not inserted anything, or we did not made any new array, or we and then we inserted that into the new node. So here we use the existing array, we use the existing data, and we made the necessary swaps based on the given data. I hope you must have learned something from this, and I will highly recommend you to watch this again if you are confused about anything. And we will also implement the code that will help you understand the heap data structure better. Special thanks to Dr. Suhail Aslam for his kindness and for the preparation of this lecture. I will see you next time. Thank you.